Hello and welcome back to Engineers Olympiad, where learning meets success. This video lecture is about the previous year questions or the years that have been asked in Indian Engineering Service exams regarding the chapter Theory of Errors in Surveying. So let's begin. This question was asked in IES 2007, and the question is: there are 10 instrument stations occupied in succession during a traverse survey. An observer makes equal error in each station, the magnitude of which is delta theta. In each instant at all the stations, what is the probable error of the final bearing at the end of the traverse? All right. So traverse survey is being conducted and there are 10 instrument stations occupied in succession, and an observer makes equal error in each station, which is equal to delta theta. Now I have to calculate the probable error of the final bearing at the end of the traverse. According to the propagation of probable errors, if addition or subtraction of a quantities is being done, then the general rule is if a computed quantity is equal to the sum of two or more observed quantities, the probable error of the computed quantity is equal to the square root of the sum of the squares of the probable errors of the observed quantities. All right. And the general expression when the probable errors in each station are same is given by this is the probable error of the traverse survey. It is equal to probable error in single observation multiplied by square root of the number of observations that have been taken. All right. So probable error of the final bearing, or I may write it, it's EF. Probable error of the final bearing is equal to probable error that has been made in each station, that is equal to plus minus delta theta. How many observations and how many instrument stations are there? There are 10 instrument stations. All right. So probable error of the final bearing is equal to plus minus all right, square root of 10 multiplied by delta theta. Alternatively, I can calculate the result as since we know that probable error in the final bearing of the line is equal to sum of the squares of the probable errors in each station, that is plus minus, if I mark each stations with the numbers 1 to 10, then it will be equal to plus E2 square plus E3 square, so on up to E10 square. All right. Then probable error in the final bearing is equal to plus minus. Each station has same magnitude of the probable error, which is equal to delta theta. That means delta theta square, so on so forth up to E10. Or the probable error in the final bearing is equal to plus minus. This is 10 times, because we have 10 instrument stations, delta theta square. Or I can write that probable error in the final bearing is equal to plus minus all right. So this is the probable error of the final bearing, which is equal to plus minus square root of 10 multiplied by the delta theta. So this was the question as asked in IES 2007. Moving on, let's do the next question. All right. So this question was asked in IES 2008. And the question is, if the weight of an angle A, which is 40 degrees and 24 minutes, is 2. Then the weight of the angle A by 3 then the weight of the angle A by 3, that is 13 degree and 28 minutes. Yeah, 13 degree 28 minutes will be. This question was asked in IAS 2008, and the question is, if the weight of an angle A is 2, angle A is 40 degree and 24 minutes, then the weight of the angle A by 3, that is 13 degree and 28 minutes, will be. We know that according to the law of weights, if a quantity of a given weight is divided by a factor, the weight of the result is obtained by multiplying its given weight by the square of that factor. All right. So if the angle A has weight of 2, according to question, then weight of A by 3 will be how much? The rule says if a quantity of a given weight is divided by a factor, the weight of the result is obtained by multiplying its given weight by the square of that factor. So first I have to take the weight of the quantity A, that is 2. Then I have to multiply with what factor the weight has been divided? 3. All right, 3. Now the weight of A by 3 will be 2 multiplied by the square of that factor by which angle has been divided. All right, so it's 2 multiplied by 3 square, which is equal to 18. All right, so the general rule for the law of weight says, I'm again illustrating that if a quantity of a given weight is divided by a factor, the weight of the result is obtained by multiplying its given weight by the square of that factor. And the factor in this case was 3, by which this angle had been divided. The weight of A is 2, and the weight of the quantity A by 3 or angle A by 3 is weight of A multiplied with the square of the factor with which it has been divided. All right, and according to the law of weights, if a quantity of a given weight is multiplied by a factor, the weight of the result is obtained by dividing its given weight by the square of that factor. All right, so if in this case we had been asked to calculate the weight of, say, 2A, then it was equal to weight of A, that is 2, divided by the square of the factor. All right, so it was 2 by 4 or 1 by 2. All right, so this was the question as asked in IAS 2008. Moving on, let's do the next question. Now, this question was asked in IAS 2009. And the question is, if every one of the 3 angles if every one of the 3 angles of a triangle if every one of the 3 angles of a triangle has a probable error of plus minus 1 seconds, then what will be the be the probable error, then what will be the probable error in the sum of the measured internal angles of a triangle. So this was the question as asked in IES 2009, and the question is, if every one of the three angles of a triangle has a probable error of plus minus 1 seconds, then what will be the probable error in the sum of the measured internal angles of a triangle, right? So we'll use the same general rule for the propagation of probable errors, and this is the case of addition of quantities. That means the probable error in the sum of the measured internal angles of a triangle is equal to the square root of the squares of the individual probable errors in each of the observed quantities. The general rule says if a computed quantity is equal to the sum of two or more observed quantities, the probable error of the computed quantity is equal to the square root of the sum of the squares of the individual probable errors of the observed quantities. All right, now here all the three angles of a triangle have the same probable error of plus minus 1 seconds. Then the probable error in the sum is equal to plus minus square root of the sum of the probable errors in the observed quantities. We have three angles in a triangle. That means it was 1 square plus 1 square 1 second square plus this, right? So probable error in the sum is plus minus 3 seconds. Alternatively, the general rule, as per the general rule, when there is equal probable error or standard error for that measure, then the general expression is that probable error in the sum is equal to the probable error in single observation or the observed quantity multiplied by square root of the number of observations. So sum each has an angle, in each of the observed quantity I have a probable error of 1 second multiplied by the square root of the number of observation. We have three angles in a triangle, so it is plus minus. All right, so this was the question as asked in IES 2009. Moving on, let's do the next question. All right, now this question was asked in IES 2014, and the question asked in IES year 2014. Question is, the measured radius of a circle, the measured radius of a circle is 80 meters with a possible error of 0.05 meters in its diameter. The possible error in the computed area will be the possible error in the computed area will be this was the question as asked in IES 2014, and the question is, the measured radius of a circle is 80 meters with a possible error of 0.05 meters in its dia. The error in the computed area will be how much? Alright, so let's solve this. We know that area of a circle is equal to pi r square. Since we have to calculate the probable error or the standard error in the computed area, as the possible error in measuring its diameter has been found to be equal to 0.05 meters. So I'll use the differentiation and then I can get the error in the computed area. So I'll differentiate this with respect to r, and this is d by dr by r square. Here it becomes d of area, or I'll write it dA in short, and here it is dA dr, here it is 2 pi and r. Alright, so dA becomes 2 pi r dr. Alright, so this becomes dA becomes 2 pi r dr. So I'll substitute the values and I'll get my answer. So the possible error in the computed area, that is dA, will be equal to 2 pi r multiplied by dr. It's 2, we'll substitute the values, 3.14. Obviously it's plus and minus. R, 80 meters multiplied by the error in diameter or radius for that matter. It is how much? 0.05 is the error in dia, but I have to calculate dr, that is 0.05 divided by 2, because the possible error in dia is 0.05 meters. That means the possible error in radius will be equal to 0.05 divided by 2. By calculations, the possible error in the computed area of the circle is equal to plus minus 12.56 meters square. So this was the question as asked in IES 2014 and we solved it. The formula or the general expression or the general method is same for calculating the effect of the errors in the observed quantities or the combined quantities, is that we find it by differentiating. Alright, the general rule says the combined effect of the errors of the observed quantities on the computed or derived quantities found by differentiating with respect to each of the observed quantities and then summing them up to obtain their total effect. Moving on, let's do the next question. Okay, next question. This question was asked in IES 2016. And the question is, the side of a square, land was measured as 150 meters and is in error by 0.05 meters. What is the corresponding error in the computed area of the land? What is the corresponding error in the computed area of the square land. Corresponding error in the computed area of the land. This question was asked in IAS 2016 and the question reads as: the side of a square land was measured as 150 meters and is in error by 0.05 meters. What is the corresponding error in the computed area of the land? We know that area of this square land is equal to side square. I'll differentiate it with respect to the side to get my effect of the error in the observed quantities in my computed or derived quantity. Here, this with respect to side is twice side. That means d of area is equal to twice of side multiplied by d of side. That means this is equal to, the corresponding error in the computed area is equal to twice of side. Twice, how much is my side? 150 meters. Multiplied by error in side is 0.05 meters. So by calculations, my corresponding error in the computed area of the land is equal to plus minus 15 meters square. So this was the question as asked in IA 2016 and we solved it. Moving on. This question was asked in IES in the year 1996. And this is an assertion reason question, and assertion is the assertion reads as: the weight of a quantity indicates the weight of a quantity indicates the relative precision within a set of observations. Within a set of observations. And the reason for this they are giving as the weights are generally taken as the weights are generally taken as directly proportional to the variance of the standard errors. To the variance of the standard errors. So this was the question as asked in IES 1996, and the question reads as, this is assertion reason question, and the question reads as: The weight assertion is the weight of a quantity indicates the relative precision within a set of observations, and the reason for this they are quoting as the weights are generally taken as directly proportional to the variance of the standard errors. Let's observe assertion first. The weight of a quantity indicates relative precision within a set of observations. This is correct statement, because we know that, as already discussed in the previous video lectures for the same chapter, theory of errors and survey, we studied that the weight of a quantity is trustworthiness of a quantity, and this weight indicates the relative precision of a quantity within a set of observations. All right, the greater the precision of an observation, the greater is its weight, and the weights are always expressed in numbers. The greater number indicates higher precision and trust as compared to the lower number. So this assertion is absolutely correct statement. The weight of a quantity indeed indicates the relative precision within a set of observations. Let's observe the reason. Second statement. The weights are generally taken as directly proportional to the variance of the standard errors is a false statement or incorrect statement, because we know that the weights are generally taken inversely proportional to the variance or square of the standard errors or probable errors. So the statement number second is wrong. The weights are generally taken as inversely proportional, not directly proportional. So the weights are inversely proportional to the variance, which is the square of standard error or probable error. So weights are never taken directly proportional to the variance. They are always taken inversely proportional to the variance or the square of the standard errors or probable errors. So assertion is correct, reason is false. So statement number, option number C, where A, assertion is correct but reason is false. All right, moving on, let's do the next question. This question was asked in IES 2001. And the question is, theory of errors and adjustments deals with minimizing the effects of theory of errors and adjustments deals with minimizing the effects of option A was instrumental errors, option B mistakes, option C systematic errors, and option D personal and accidental errors. Personal and accidental errors. So this question was asked in IES 2001. And the question is, theory of errors and adjustments deals with minimizing the effects of instrumental errors, mistakes, systematic errors, or personal and accidental errors. We know that in any measurement, random or accidental errors or compensating errors do not disappear whatever precautions are being taken. So these errors obey the laws of chance and hence they are handled with the help of theory of probability. So therefore theory of errors and adjustment deals with personal errors and accidental errors. And it's always assumed that all the mistakes and the systematic errors are eliminated from the given set of observations, right? We always assume that all the mistakes or gross errors or systematic errors are eliminated before this system. So theory of errors and adjustment deals with the personal and accidental errors or random errors or compensating errors. Moving on, let's do the next question. This question was asked in IES 2003. IES 2003, and the question is, from the probability equation, from the probability equation, it is found that the from the probability equation it is found that the most probable values of series of errors arising out of the observations of equal weightage are those for which the sum of their squares is option A 0, B infinity, C is minimum, and D is maximum. This was the question as asked in IES 2003, and the question is, from the probability equation it is found that the most probable values of series of errors arising out of the observations of equal weightage are those for which the sum of their squares is. We know that according to the theory of least squares, if the measurements are of equal weight, the most probable value is that which makes the sum of the squares of the residuals a minimum. Alright, so according to the theory of least squares, if the measurements are of equal weight, then the most probable value is that which makes the sum of the squares of the residual or the residual error or the variation a minimum. So the answer is option C. Option C is the correct answer, because according to the theory of least squares, if the measurements are of equal weight, the most probable value is that value which makes the sum of squares of residual a minimum. And for the observations of different weight, we have the theory. Theory says that if the measurements are of unequal weights, the most probable value is that which makes the sum of the products of the weight and the squares of the residual a minimum. Thus, for that case, we have this is the case for the observations having equal weight, and this is the case for the observations having unequal weights. And the theory of least squares for the observations having unequal weights says that if the measurements are of unequal weights, the most probable value is that which makes the sum of the products of weight and the squares of the residuals a minimum. So this was about the theory of the least squares and the question as asked in IES 2003. With this, we conclude this video lecture. Thank you for watching.